Hey everyone, and welcome back to The Explainer. Today we are visualizing the wildly complex world of chemical separations. I mean, if you've ever wondered how scientists actually figure out exactly what's inside a complex mixture, literally down to the exact molecule, well, you're in the right place. We're going to break down the science of chromatography step by step. So let's just jump right in. So first off, how do scientists measure the invisible? Think about it. When you have a complex liquid or a gas, you obviously can't just look at it with your naked eye and, tally up the molecules. You need a way to spread them all out. You have to make the invisible entirely visible. And honestly, that's the real magic of analytical chemistry, and specifically, the incredible tool we're decoding today. Okay, let's start with the basics, the chromatogram. Now, the word itself might sound a little intimidating, but it's really just a two-dimensional diagram. On the horizontal axis, we usually track time, or sometimes the fluid volume. And on the vertical axis, that's where we track a signal from a detector that tells us the exact instant a specific substance, which we call a solute, exits our testing column. It is, quite literally, a physical map of time versus concentration.
All right, moving to section 1, the ideal, mathematical perfection.
Now, consider this foundational idea. The features of an ideal chromatogram are the same as those obtained from a normal distribution of random errors. This is huge. Why? Because it means the foundation of our ideal chemical model isn't actually based on some obscure, super complex chemical law. Nope. It's rooted in classic statistics. It is literally the standard probability density function. You know, the famous Gaussian bell curve you probably remember from high school math class. And when we map out that perfect mathematical equation, we hit a very specific magic number, 0.399. And our ideal probability density function, when our x value, which represents the exact center point of our eluting chemical, is precisely at 0, the absolute maximum height of our curve hits exactly 0.399. It perfectly represents the densest cluster of our target molecules exiting the analytical column at exactly the same microsecond. And this brilliantly illustrates that concept. Notice the inflection points on this bell curve. They sit right at exactly 60.6% of the maximum peak height. And the base of the curve, its width is precisely 4 standard deviations, or 4 sigma. Basically, in an ideal world, 95.4% of your chemical compound sits beautifully right there between -2 and +2 standard deviations. It's just pure symmetrical perfection. But here is the absolute crucial takeaway. In an ideal, mathematically perfect case, the retention time, meaning the time a compound takes to travel through and actually exit the column, is completely independent of how much of it you inject. Seriously, whether you put in a tiny microscopic drop or a massive concentrated dose, the peak maximum is going to hit the detector at the exact same moment. It acts like a completely reliable, unchanging clock. Which brings us to section 2. The reality, chemistry in motion. So, as you might guess, out in the real world, our perfect bell curve gets pretty distorted. But why? Well, think of a chemical moving through a physical column, kind of like traffic on a highway. The fluid right in the center of the column, the fast lane, moves at maximum speed. But the fluid scraping against the physical walls of the column, its speed is practically 0. It's totally stuck in traffic. Add in some irregular concentrations when you first inject the sample, and suddenly our molecules are definitely not exiting all at once. The curve stretches out, and the whole shape deforms. Now, what's really interesting here is how we can visualize exactly how that distortion happens. Over on the left, we have the ideal linear isotherm. That's our perfect symmetrical peak. But in the middle, check out the convex curve. This happens when the column is overloaded and completely saturated. The front of a chemical peak rushes out really fast, but the tail drags behind, so it leans heavily to the right. And then on the far right, the concave curve shows the exact opposite scenario. The analyte is strongly retained by the column, so the front drags slowly and the tail drops off sharply, so it leans left. To actually manage this messy reality, scientists need a way to measure the mess itself. So we anchor reality back to the model by contrasting our perfect symmetry with what's called the mathematical skewing factor. Measured really low down at just 10% of the peak's height, analysts compare the back half of the peak to the front half. If that ratio isn't exactly 1, well, we've lost our perfect Gaussian symmetry, and the math has to adapt to the physical reality of the situation. All right, let's dive into section 3, achieving perfect resolution. So, how do we fix it? The answer lies in the resolution factor, or R.
For chromatographers, this is the absolute holy grail. It's a strict metric used to quantify exactly how well two adjacent chemical peaks are separated from one another. It factors in both the time the peaks exit and how wide they've spread out at their bases. Ultimately, if R is too low, your peaks overlap, and honestly, your data becomes completely useless. Let's see how this builds visually. Look at this graph showing baseline resolution. This magical moment happens when the resolution factor hits exactly 1.5. At this specific point, the valley between the two chemical peaks dips down so low that it doesn't exceed 2% of the peak height. This means you can clearly, definitively tell you have two completely separate compounds, and you can measure them accurately. But getting to that magic R value of 1.5, yeah, that's a constant tug of war. Welcome to the chromatographer's triangle. An optimized separation is basically a permanent conflicting battle between three parameters: resolution, speed, and capacity. If you want perfect resolution, you're probably going to have to sacrifice speed, making your analysis painfully slow. But if you want to push a high capacity of chemicals through the instrument really quickly, your resolution is just going to collapse. It is an incredibly delicate, precise balancing act.
So what actually happens when you just can't win that battle? What if the peaks stubbornly overlap no matter how much you physically optimize things? Well, enter modern software. When physical chemistry and fluid dynamics fail to give us that clean separation, software deconvolution totally comes to the rescue. It takes that messy, overlapping signal and mathematically splits it right back apart into those perfect, individual Gaussian components we started this explainer with. It essentially calculates the hidden areas perfectly, using code instead of chemistry.
Which leaves us with a fascinating, almost philosophical question to wrap things up. When physical chemistry fails, how does fuzzy logic software artificially separate what the physical column couldn't? I mean, are we still measuring hard chemical reality? Or are we increasingly relying on mathematical algorithms to construct an ideal world that doesn't actually exist inside the tube? It's definitely something to ponder as we keep blending physical science with digital computing. Thank you so much for exploring the chromatogram with me today, and as always, keep questioning the data.